Hello, beautiful souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. Dreams are experiences that occur during sleep, and they represent a form of mental activity that takes place when the body is at rest and the external environment is no longer being actively processed by the waking brain. When we talk about dreams in the context of scientific research, we are referring to a specific type of brain activity that can be measured and observed through various technologies and methods that allow researchers to examine what happens inside the brain during different stages of sleep. Dreams are not mystical events or messages from another realm, but rather they are biological processes that emerge from the ordinary functioning of the nervous system during the sleep cycle. And this means that dreams can be studied in much the same way that other brain functions are studied, through careful observation, measurement, and analysis of the patterns of neural activity that occur during the hours when a person is asleep. In scientific research, dreams are understood as a form of conscious experience that occurs during sleep, and this experience involves the generation of images, sounds, sensations, thoughts, and emotions that seem to unfold in a way that resembles waking life, even though the person experiencing the dream is not awake and is not interacting with the actual external world. The scientific definition of dreaming focuses on the fact that dreams are produced by the brain itself, without input from the outside environment. And this makes dreams a type of internally generated mental activity that reflects the brain's ongoing work. During sleep, researchers who study dreams are interested in understanding how the brain creates these experiences, what parts of the brain are involved in the process, and what functions dreams might serve in terms of memory, learning, emotional processing, and other aspects of mental life. When we consider what dreams mean in the context of scientific research, we are not asking about symbolic meanings or hidden messages, but rather we are asking about the biological mechanisms that give rise to dreams and the role that dreams play In the overall functioning of the brain and body, dreams are a natural part of the sleep cycle, and they occur in most people on a regular basis. Although not all people remember their dreams, and not all dreams are equally vivid or complex, the study of dreams involves examining the brain activity that occurs during sleep, the stages of sleep in which dreams are most likely to occur, and the ways in which dreams relate to other cognitive processes, such as memory consolidation, emotional regulation, and sensory processing. The biological definition of dreaming emphasizes that dreams are a form of brain activity that takes place during sleep, and this activity involves the activation of various brain regions that are responsible for generating sensory experiences, emotions, thoughts, and memories. During dreaming, the brain is not simply resting or inactive, but rather it is engaged in a complex set of processes that involve the firing of neurons, the release of neurotransmitters, and the coordination of activity across different brain areas. Dreams are produced by the same neural systems that are active during waking life, including the visual cortex, the auditory cortex, the motor cortex, the limbic system, and the prefrontal cortex. Although the patterns of activity in these regions during sleep are different from the patterns that occur during waking consciousness, the brain during dreaming is in a state that is distinct from both waking consciousness and deep, dreamless sleep, and this state is characterized by a unique combination of neural activity that allows for the generation of vivid sensory experiences and emotional responses, even though the person is not awake and is not receiving input from the external world. The biological processes that underlie dreaming involve the spontaneous activation of neural networks that are involved in perception, memory, emotion, and cognition, and these networks work together to create the subjective experience of a dream, which may include visual images, sounds, physical sensations, and emotional feelings that seem real to the person experiencing the dream, even though they are entirely generated by the brain's internal activity. The difference between dreaming and waking thought is a topic that has been studied extensively by neuroscientists and sleep researchers. And one of the key differences is that during waking thought, the brain is actively processing information from the external environment, receiving input from the senses, and using this information to guide behavior and decision-making, whereas during dreaming, the brain is largely disconnected from the external environment and is instead generating experiences based on internal patterns of neural activity. During waking consciousness, the prefrontal cortex, which is the part of the brain responsible for executive functions such as planning, reasoning, self-awareness, and logical thinking, is highly active and plays a central role in organizing thoughts, evaluating information, and making decisions. However, during dreaming, the prefrontal cortex is much less active, and this reduced activity in the prefrontal cortex is one of the reasons why dreams often lack the logical structure and self-awareness that characterize waking thought. Another difference between dreaming and waking thought is that during waking consciousness, the brain's attentional systems are focused on the external environment, allowing the person to respond to sensory input, navigate the physical world, and interact with other people. Whereas during dreaming, the brain's attentional systems are turned inward, focusing on internally generated images, thoughts, and emotions, rather than on external stimuli. This shift in attention from the external to the internal is associated with changes in brain activity that can be observed using neuroimaging techniques, and these changes reflect the fact that during dreaming, the brain is operating in a different mode than it does during waking life. The sensory input that the brain receives during dreaming comes not from the external world, but from the brain's own memory systems and neural networks. And this internal sensory input is what gives rise to the vivid images and sensations that characterize dreams. Waking thought is also characterized by a high degree of voluntary control, meaning that during waking consciousness, a person can direct their attention, choose what to think about, and make deliberate decisions about how to respond to situations. Whereas during dreaming, there is much less voluntary control over the content and flow of mental activity, and the person experiencing the dream typically has little or no ability to direct the dream or to choose What happens in the dream? This lack of voluntary control during dreaming is related to the reduced activity in the prefrontal cortex, which is the brain region that is responsible for executive control and decision-making. During dreaming, the brain's activity is more automatic and less regulated by conscious control, and this allows for the spontaneous generation of images, thoughts, and emotions that may not follow the logical rules that govern waking thought. Brain activity patterns associated with dreams have been studied using a variety of neuroimaging techniques, including electroencephalography, which measures the electrical activity of the brain, and functional magnetic resonance imaging, which measures changes in blood flow to different brain regions. And these studies have revealed that during dreaming, there are specific patterns of brain activity that are distinct from the patterns observed during waking consciousness and during non-dreaming sleep. One of the most consistent findings from research on brain activity during dreaming is that the visual cortex, which is the part of the brain responsible for processing visual information, is highly active during dreams, and this high level of activity in the visual cortex is thought to be responsible for the vivid visual imagery that is a common feature of dreams. The visual cortex during dreaming shows patterns of activity that are similar to the patterns observed when a person is awake and looking at visual stimuli, even though during dreaming the eyes are closed and there is no actual visual input from the external world. In addition to the visual cortex, other brain regions that are active during dreaming include the limbic system, which is involved in emotion and motivation, and the hippocampus, which plays a key role in memory formation and retrieval. The limbic system is particularly active during dreams, and this high level of activity in the limbic system is thought to be responsible for the emotional content of dreams, which often includes strong feelings such as fear, joy, anxiety, or sadness. The hippocampus, which is a structure located in the medial temporal lobe of the brain is also active during dreaming, and the hippocampus is thought to play a role in the retrieval of memories that are incorporated into dreams, as well as in the consolidation of memories during sleep. The activity of the hippocampus during dreaming reflects the fact that dreams often include elements from past experiences, and the hippocampus is the brain region that is responsible for linking together different memories and creating a sense of continuity in mental experience. The prefrontal cortex, which is the part of the brain responsible for higher-order cognitive functions, such as planning, reasoning, and self-awareness, shows reduced activity during dreaming compared to waking consciousness. And this reduced activity in the prefrontal cortex is one of the key differences between the brain activity patterns observed during dreaming and those observed during waking thought. The reduced activity in the prefrontal cortex during dreaming is thought to be responsible for several characteristic features of dreams, including the lack of logical structure, the reduced self-awareness, and the inability to recognize that one is dreaming. The prefrontal cortex during waking consciousness acts as a kind of supervisor or monitor that evaluates incoming information, checks for logical consistency, and maintains a sense of self-awareness. But during dreaming, this supervisory function is greatly diminished, and the brain operates in a more spontaneous and unregulated manner. The motor cortex, which is the part of the brain responsible for controlling voluntary movements, also shows activity during dreaming, and this activity in the motor cortex is thought to be related to the experience of movement in dreams, such as walking, running, or performing other actions. However, during dreaming, the motor cortex is not actually controlling the muscles of the body, because during sleep, there is a mechanism that inhibits the transmission of motor commands from the brain to the muscles, and this mechanism prevents the person from acting out the movements that occur in their dreams. This inhibition of motor output during sleep is an important safety mechanism that prevents people from injuring themselves or others while they are asleep and dreaming, and in some sleep disorders, this inhibition mechanism is impaired, which can lead to people physically acting out their dreams. REM sleep, which stands for rapid eye movement sleep, is the stage of sleep in which the most vivid and memorable dreams occur, and REM sleep is characterized by a unique pattern of brain activity that includes high-frequency brain waves, rapid movements of the eyes beneath the closed eyelids, and a general increase in brain activity that makes the brain during REM sleep appear almost as active as it is during waking consciousness. REM sleep occurs in cycles throughout the night, with each cycle of REM sleep lasting anywhere from a few minutes to about half an hour, and the amount of time spent in REM sleep typically increases as the night progresses, so that the longest and most intense periods of REM sleep occur in the early morning hours before waking. During REM sleep, the brain is highly active, but the body is in a state of muscle atonia, which means that most of the voluntary muscles are temporarily paralyzed, and this paralysis prevents the person from acting out the movements that occur in their dreams. The brain activity during REM sleep is characterized by a pattern of electrical activity that is similar to the pattern observed during waking consciousness, with high-frequency, low-amplitude brain waves that indicate a high level of neural activity and information processing. The regions of the brain that are most active during REM sleep include the visual cortex, the limbic system, the hippocampus, and the brainstem, while the prefrontal cortex shows reduced activity compared to waking consciousness. The high level of activity in the visual cortex during REM sleep is thought to be responsible for the vivid visual imagery that characterizes REM dreams, and the high level of activity in the limbic system is thought to be responsible for the emotional intensity of REM dreams. The brainstem, which is the part of the brain that controls basic physiological functions such as breathing and heart rate, plays a key role in initiating and maintaining REM sleep, and the brainstem sends signals to other parts of the brain that trigger the characteristic features of REM sleep, including the rapid eye movements, the muscle atonia, and the high-frequency brain activity. REM sleep is thought to play a role in several important functions, including memory consolidation, emotional processing, and brain development, and the dreams that occur during REM sleep may be a byproduct of these underlying brain processes. The memory consolidation that occurs during REM sleep involves the strengthening of connections between neurons that were formed during waking experiences, and this strengthening of neural connections is thought to help stabilize memories and integrate new information with existing knowledge. The emotional processing that occurs during REM sleep may involve the reactivation of emotional memories and the regulation of emotional responses, and the dreams that occur during REM sleep may reflect this ongoing emotional processing, as dreams often include emotional content and may help the brain to process and regulate emotions in a way that supports emotional well-being. Non-REM sleep, which includes all the stages of sleep that are not REM sleep, is divided into several stages that range from light sleep to deep sleep, and each stage of non-REM sleep is characterized by a different pattern of brain activity. The early stages of non-REM sleep, which are sometimes called light sleep, are characterized by a slowing of brain activity and a gradual disengagement from the external environment, while the later stages of non-REM sleep, which are sometimes called deep sleep or slow-wave sleep, are characterized by very slow, high-amplitude brain waves that indicate a low level of neural activity and a deep state of rest. During non-REM sleep, the brain is less active overall compared to REM sleep, and waking consciousness and the prefrontal cortex, the limbic system, and the sensory cortices all show reduced activity compared to their activity levels during REM sleep and waking consciousness. Dreams or dreamlike experiences can occur during non-REM sleep, although these experiences are generally less vivid, less complex, and less memorable than the dreams that occur during REM sleep. Non-REM dreams tend to be more thought-like and less sensory than REM dreams, and they often involve simple thoughts, fragments of memories, or vague impressions, rather than the elaborate narratives and vivid imagery that characterize REM dreams. The brain activity during non-REM sleep is characterized by slow, synchronized oscillations in neural activity, and these slow oscillations are thought to play a role in memory consolidation and the restoration of brain function. The slow wave activity that occurs during deep non-REM sleep is associated with the consolidation of declarative memories, which are memories for facts and events, and the slow oscillations in brain activity during non-REM sleep may help to transfer information from the hippocampus, which is involved in the initial encoding of memories, to the cortex, which is involved in the long-term storage of memories. The experiences that occur during non-REM sleep are often difficult to recall upon waking, and when people are awakened from non-REM sleep and asked about their mental experiences, they often report that they were thinking about something, or that they had some vague sense of mental activity, but they are less likely to report vivid, story-like dreams compared to when they are awakened from REM sleep. The reduced vividness and complexity of non-REM dreams may be related to the lower level of brain activity during non-REM sleep, and particularly to the reduced activity in the visual cortex and the limbic system, which are the brain regions that are responsible for generating vivid sensory experiences and emotional responses. The brain, during deep non-REM sleep, is in a state of rest and restoration, and the mental experiences that occur during this stage of sleep reflect the brain's low level of activity and its focus on restorative processes rather than on the generation of complex mental content. Memory activation during dreams is a topic that has been studied extensively by researchers interested in understanding how the brain processes and consolidates memories during sleep. During dreaming, the brain reactivates patterns of neural activity that were formed during waking experiences, and this reactivation of memories is thought to play a role in the consolidation and integration of new information with existing knowledge. The memories that are reactivated during dreams may include recent experiences, older memories, or fragments of different memories that are combined in novel ways, and the content of dreams often reflects this reactivation of memory traces. The hippocampus, which is a brain structure that is critical for the formation of new memories and the retrieval of existing memories, plays a key role in the memory activation that occurs during dreams, and the hippocampus is thought to coordinate the reactivation of memory traces across different brain regions during sleep. During waking life, when a person has an experience, the brain encodes that experience by forming patterns of neural activity that involve multiple brain regions, including sensory cortices that process sensory information, the hippocampus that links together different aspects of the experience, and the prefrontal cortex that organizes and evaluates the information. These patterns of neural activity represent the memory of the experience, and during sleep, the brain spontaneously reactivates these patterns, which allows the the memory to be strengthened and stabilized through a process called consolidation. The reactivation of memories during sleep occurs in both REM sleep and non-REM sleep, although the types of memories that are consolidated during each stage of sleep may differ, with non-REM sleep being particularly important for the consolidation of declarative memories, and REM sleep being particularly important for the consolidation of procedural memories and emotional memories, the memories that are incorporated into dreams are not perfect replicas of the original experiences, but rather they are reconstructed and transformed by the brain's ongoing activity during sleep. And this is why dreams often include distorted, exaggerated, or bizarrely combined elements from different memories. The process of memory reactivation during dreams is thought to involve the spontaneous firing of neurons in the hippocampus and other brain regions, and this spontaneous neural activity leads to the activation of memory traces that are then experienced as part of the dream. The fact that dreams often include elements from recent experiences, sometimes called the day residue effect, suggests that the brain preferentially reactivates memories of recent events during sleep, possibly because these memories are still in the process of being consolidated and integrated with existing knowledge. The role of the hippocampus in dream formation is central to our understanding of how dreams are generated and what function they might serve in the overall processing of memories and experiences. The hippocampus is a seahorse-shaped structure located in the medial temporal lobe of the brain, and it is one of the most important brain regions for learning and memory. The hippocampus is involved in the encoding of new memories, the retrieval of existing memories, and the spatial navigation that allows organisms to orient themselves in their environment. During sleep, the hippocampus remains active, and it continues to process information and reactivate memory traces that were formed during waking life. The activity of the hippocampus during sleep is thought to be critical for the consolidation of memories, which is the process by which newly formed memories are stabilized and integrated into long-term storage. During dreaming, the hippocampus is thought to play a role in selecting and activating memories that are incorporated into the dream. And the hippocampus may also play a role in linking together different memories and creating the narrative structure of dreams. Although the narrative structure of dreams is often fragmented and illogical compared to waking thought, the hippocampus communicates with other brain regions during sleep, including the cortex and the limbic system, and these communications allow for the coordinated reactivation of memory traces across different brain areas. The patterns of activity in the hippocampus during sleep include replay activity, which is the spontaneous reactivation of sequences of neural activity that occurred during waking experiences. And this replay activity is thought to help strengthen the neural connections that represent memories. The hippocampus during REM sleep shows a different pattern of activity compared to its activity during non-REM sleep, and the activity of the hippocampus during REM sleep is characterized by theta oscillations, which are rhythmic patterns of neural activity at a frequency of about 4 to 8 cycles per second. These theta oscillations in the hippocampus during REM sleep are similar to the theta oscillations that occur in the hippocampus during waking activities that involve active exploration and learning, and the presence of theta oscillations during REM sleep suggests that the hippocampus during REM sleep is engaged in processes that are related to learning and memory consolidation. The theta oscillations may help to coordinate the activity of neurons in the hippocampus and facilitate the reactivation and strengthening of memory traces during REM sleep. The role of the hippocampus in dream formation is also related to its role in creating associations between different memories and in generating novel combinations of familiar elements. And this may be one reason why dreams often include unexpected or bizarre juxtapositions of people, places, and events from different times and contexts. The hippocampus is particularly good at forming associations between different pieces of information, and during sleep, the hippocampus may spontaneously activate these associations, leading to the creation of dream content that combines elements from different memories in ways that would not normally occur during waking thought. The associative nature of hippocampal processing may help to explain why dreams can be so creative and why they often include surprising connections between seemingly unrelated ideas or experiences. Emotional processing in dreams is another aspect of dreaming that has been studied by neuroscientists and sleep researchers, and the emotional content of dreams is one of the most salient features of the dreaming experience. Dreams often include strong emotions, and the emotions experienced in dreams can range from positive feelings such as joy and excitement to negative feelings such as fear, anxiety, and sadness. The emotional intensity of dreams is thought to be related to the high level of activity in the limbic system during REM sleep, and the limbic system is a network of brain structures that includes the amygdala, the hippocampus, and several other regions that are involved in emotion, motivation, and memory. The amygdala, which is an almond-shaped structure located deep in the brain, plays a particularly important role in processing emotions, and especially in processing fear and other negative emotions. During REM sleep, the amygdala is highly active, and this high level of activity in the amygdala is thought to be responsible for the emotional content of REM dreams. The amygdala during REM sleep processes emotional memories and may help to regulate emotional responses by reactivating emotional experiences in a safe context where the person is asleep and not exposed to actual threats or challenges. The reactivation of emotional memories during sleep may help the brain to process and integrate emotional experiences, and this processing may contribute to emotional regulation and psychological well-being. The emotional processing that occurs during dreams may also help to reduce the emotional intensity of memories over time, so that experiences that were initially very emotionally arousing become less intense as they are processed and integrated during sleep. The prefrontal cortex, which is involved in the regulation and control of emotions during waking consciousness, shows reduced activity during REM sleep, and this reduced activity in the prefrontal cortex may be one reason why the emotions experienced in dreams are often more intense and less well regulated than the emotions experienced during waking life. During waking consciousness, the prefrontal cortex helps to modulate emotional responses by evaluating situations, putting emotions into context, and applying cognitive strategies to manage emotional reactions. However, during dreaming, the reduced activity in the prefrontal cortex means that emotions are less regulated by cognitive control, and this may allow for a more direct and intense experience of emotions during dreams. The combination of high limbic activity and low prefrontal activity during REM sleep creates a brain state in which emotional processing is heightened but not subject to the same level of cognitive control that occurs during waking consciousness. The emotional processing that occurs during dreams is thought to serve an adaptive function by helping the brain to integrate emotional experiences and to prepare for future emotional challenges. Some researchers have proposed that the emotional content of dreams reflects the brain's ongoing work of processing and regulating emotions during sleep. The experiences that a person has during waking life, especially emotionally significant experiences, are reactivated during sleep, and this reactivation allows the brain to process the emotional aspects of these experiences in a way that may help to reduce their emotional impact and to integrate them with existing knowledge and emotional schemas. The fact that dreams often include scenarios that are emotionally challenging or that involve working through emotional conflicts may reflect the brain's attempt to process and resolve emotional issues during sleep. Visual and sensory simulation during dreaming is one of the most distinctive features of the dreaming experience, and the vividness of the sensory experiences in dreams is comparable to the sensory experiences that occur during waking life, even though during dreaming the sensory input is entirely generated by the brain's internal activity rather than by stimulation from the external environment. The visual imagery in dreams is particularly vivid, and many people report that the visual experiences in their dreams are as clear and detailed as the visual experiences they have while awake, with colors, shapes, movements, and scenes that seem entirely real. The visual cortex, which is located at the back of the brain and is responsible for processing visual information, is highly active during REM sleep, and this high level of activity in the visual cortex is what generates the vivid visual imagery of dreams during waking life. The visual cortex receives input from the eyes, and this input is processed by neurons in the visual cortex to create the experience of seeing the world during dreaming. However, the eyes are closed and there is no input from the external environment, but the visual cortex is still active, and this activity is driven by signals from other brain regions rather than by input from the eyes. The visual cortex during dreaming is activated by signals from the brainstem and from memory systems in the brain, and these signals cause neurons in the visual cortex to fire in patterns that generate visual experiences. The visual imagery in dreams is thus a form of internally generated simulation in which the brain creates visual experiences based on stored memories and spontaneous neural activity rather than on actual visual input from the environment. In addition to visual imagery, dreams can also include auditory experiences, tactile sensations, and sometimes even taste and smell. Although visual experiences are the most common and most vivid sensory modality in dreams, auditory experiences in dreams can include hearing voices, music, or other sounds, and these auditory experiences are generated by activity in the auditory cortex, which is the part of the brain responsible for processing sound. Tactile sensations in dreams can include feelings of touch, pressure, pain, or temperature, and these sensations are generated by activity in the somatosensory cortex, which is the part of the brain responsible for processing touch and bodily sensations. The fact that dreams can include such a wide range of sensory experiences suggests that the brain during dreaming is capable of simulating the full range of sensory experiences that occur during waking life, and this sensory simulation is one of the reasons why dreams can feel so real and immersive. The sensory simulation that occurs during dreaming is thought to involve the reactivation of sensory memories, which are memories that include specific sensory details, such as the appearance of a person's face, the sound of a familiar voice, or the feeling of a particular texture. When the brain reactivates these sensory memories during sleep, it recreates the sensory experiences that were part of the original memory And this recreation of sensory experiences is what gives rise to the vivid sensory content of dreams. The sensory simulation in dreams is not always accurate or realistic, and dreams often include distorted or exaggerated sensory experiences. But the basic mechanism of sensory simulation in dreams is the same mechanism that is used during waking life to generate sensory experiences based on external input, except that during dreaming, the input comes from the brain's internal memory systems rather than from the external world. Why dreams often lack logical structure is a question that has been addressed by researchers who study the cognitive characteristics of dreaming, and the lack of logical structure in dreams is one of the most striking differences between dreaming and waking thought. During waking consciousness, thoughts and experiences are organized according to logical rules and causal relationships, and the prefrontal cortex plays a key role in maintaining this logical structure by evaluating information, checking for consistency, and organizing thoughts in a coherent manner. However, during dreaming, the prefrontal cortex is much less active, and this reduced activity in the prefrontal cortex is one of the main reasons why dreams often lack the logical structure that characterizes waking thought. The logical inconsistencies in dreams can take many forms, including sudden changes in scene or context, the presence of impossible or implausible events, the appearance of people or objects that change their identity or form, and the occurrence of events that do not follow normal causal relationships. In a dream, a person might find themselves in one location and then suddenly be in a completely different location without any transition, or they might encounter a person who is simultaneously familiar and unfamiliar, or they might experience events that violate the laws of physics, or the rules of everyday reality. These logical inconsistencies are so common in dreams that they are considered one of the defining characteristics of the dreaming state. And yet, during the dream, the person experiencing these inconsistencies often does not notice that anything is strange or impossible. The reason why people do not notice the logical inconsistencies in their dreams is related to the reduced activity in the prefrontal cortex, which is the brain region responsible for critical thinking, logical reasoning, and reality monitoring. During waking consciousness, the prefrontal cortex constantly evaluates incoming information and checks it against stored knowledge and expectations, and this monitoring function allows people to detect errors, notice inconsistencies, and recognize when something does not make sense. However, during dreaming, the prefrontal cortex is not performing this monitoring function, or is performing it at a much reduced level. And this means that the brain, during dreaming, does not evaluate the content of the dream for logical consistency or plausibility. The lack of critical evaluation during dreaming allows the dream to unfold in a way that is guided more by associative connections and emotional themes than by logical rules or realistic constraints. The logical structure of dreams is also influenced by the way that memories are activated and combined during sleep, and the associative nature of memory retrieval during dreaming means that elements from different memories can be combined in ways that do not follow the logical or temporal relationships that existed in the original experiences. The hippocampus, which plays a key role in memory retrieval during dreaming, is particularly good at forming associations between different memories based on shared features or emotional themes. And during dreaming, the hippocampus may activate multiple memories simultaneously and combine them into a single dream narrative, even if those memories are from different times, places, or contexts. This associative combination of memories can result in dream content that is logically inconsistent, but thematically coherent, with elements that are related by their emotional significance or by superficial similarities, rather than by logical connections. Reduced self-awareness during dreams is another characteristic feature of the dreaming state, and during most dreams, people have little or no awareness that they are dreaming. They experience the events of the dream as if they were real events happening in waking life. This lack of self-awareness during dreaming is sometimes referred to as a lack of metacognition, which is the ability to reflect on one's own mental states and to recognize the nature of one's current experience. During waking consciousness, people have a high degree of metacognitive awareness, and they know that they are awake, that they are thinking certain thoughts, and that their experiences are the result of their interaction with the real world. However, during most dreams, this metacognitive awareness is absent or greatly reduced, and the person experiencing the dream does not recognize that they are asleep and dreaming. The reduced self-awareness during dreams is related to the reduced activity in the prefrontal cortex, which is the brain region that is responsible for self-reflection, introspection, and metacognitive monitoring. The prefrontal cortex during waking consciousness maintains a sense of self-awareness by continuously monitoring mental activity and comparing it with stored knowledge about the self and the world. And this monitoring function allows people to maintain a coherent sense of identity and to recognize their current mental state. However, during dreaming, the prefrontal cortex is much less active, and this reduced activity means that the brain is not performing the metacognitive monitoring that would allow the person to recognize that they are dreaming. The lack of prefrontal activity during dreaming also means that people have reduced awareness of their goals, intentions, and long-term plans while dreaming, and they may act in ways during dreams that are inconsistent with their waking values or intentions without noticing the inconsistency. In some dreams, people do become aware that they are dreaming, a phenomenon known as lucid dreaming. During lucid dreams, the person has metacognitive awareness and recognizes that the experience they are having is a dream rather than waking reality. Lucid dreaming is associated with increased activity in the prefrontal cortex compared to non-lucid dreaming, and the increased prefrontal activity during lucid dreams is thought to be what allows the person to have metacognitive awareness and to recognize that they are dreaming. However, lucid dreams are relatively rare compared to non-lucid dreams, and most dreams occur without any awareness on the part of the dreamer that they are in a dream state. The reduced self-awareness during non-lucid dreams is a normal feature of the dreaming brain state, and it reflects the overall pattern of brain activity during sleep, with reduced activity in the prefrontal regions that support metacognition and increased activity in the sensory and emotional regions that generate dream content. The brain's monitoring systems during sleep operate at a reduced level compared to their activity during waking consciousness, and this reduced monitoring is part of what allows sleep to occur and what gives dreaming its distinctive characteristics. During waking consciousness, the brain's monitoring systems are constantly evaluating sensory input, checking for potential threats or opportunities, maintaining awareness of the body and the environment, and ensuring that thoughts and actions are appropriate and goal-directed. These monitoring functions involve multiple brain regions, including the prefrontal cortex, the anterior cingulate cortex, and various sensory and motor areas, and they require a significant amount of neural resources and attention during sleep. These monitoring systems are down-regulated, meaning that they are less active and less responsive, and this downregulation is necessary for the brain to enter the state of reduced consciousness that characterizes sleep. The reduced monitoring during sleep means that the brain is less responsive to external stimuli, and sensory input from the environment is largely filtered out or ignored during sleep, allowing the person to remain asleep even in the presence of moderate levels of noise, light, or other environmental stimulation. The sensory systems during sleep are not completely inactive, and the brain continues to process some sensory information and can respond to particularly salient or threatening stimuli, such as a loud noise or a touch. But the threshold for waking is higher during sleep than during waking consciousness, and most sensory input is not sufficient to cause arousal or to enter conscious awareness. The reduced monitoring of sensory input during sleep is part of what allows the brain to focus on internal processes such as memory consolidation and restoration, rather than on processing information from the external environment. The monitoring of internal states during sleep is also reduced, and this includes reduced monitoring of bodily sensations, reduced monitoring of thought processes, and reduced monitoring of the logical consistency and plausibility of mental content. The lack of internal monitoring during sleep is what allows dreams to include impossible or implausible events without the dreamer recognizing that anything is amiss. And it is also what allows the dreamer to accept the strange and often nonsensical content of dreams as if it were perfectly normal. The reduced internal monitoring during sleep is related to the reduced activity in the prefrontal cortex and other brain regions that are involved in executive control and metacognitive awareness. And this reduced activity is a normal and necessary part of the sleep state. The brain's monitoring systems begin to become more active as sleep lightens, and as the person approaches waking, and the gradual increase in monitoring activity is part of what allows the transition from sleep to wakefulness to occur. During the early morning hours, when sleep is lighter and more fragmented, the brain's monitoring systems may be more active than during the deeper sleep of the early night. And this increased monitoring may be one reason why dreams during the early morning are often more complex, more vivid, and more easily remembered than dreams from earlier in the night. The transition from sleep to waking involves a gradual reactivation of the brain's monitoring systems. And as these systems come back online, the person becomes more aware of their body, their environment, and their own thoughts. And the dream state fades as waking consciousness returns. Why dreams fade after waking is a common experience for most people. And it is not unusual for a person to wake up with a vivid memory of a dream, only to find that the details of the dream rapidly fade and become difficult to recall within a few minutes of waking. The fading of dreams after waking is related to the way that memories are encoded and stored in the brain, and to the differences between the brain state during sleep and the brain state during waking consciousness. Dreams are generated by patterns of neural activity that occur during sleep. And these patterns of activity are not always transferred into long-term memory in a stable form, which means that dream memories are often fragile and prone to rapid forgetting. One reason why dreams fade so quickly after waking is that during sleep, the brain is in a neurochemical state that is not optimal for the formation of long-term memories. And the neurotransmitters that are involved in memory consolidation, such as norepinephrine and serotonin, are present at lower levels during REM sleep compared to waking consciousness. The reduced levels of these neurotransmitters during REM sleep may make it more difficult for the brain to encode dream experiences into stable, long-term memories. And this may be one reason why dreams are so easily forgotten. The hippocampus, which plays a key role in the formation of long-term memories, is active during dreaming and is involved in generating dream content. But the patterns of activity in the hippocampus during dreaming are different from the patterns that occur during waking experiences. And these differences may affect how well dream memories are encoded. Another reason why dreams fade after waking is that when a person wakes up, their attention quickly shifts to the waking environment and to the concerns and activities of waking life. This shift in attention can interfere with the consolidation and retrieval of dream memories. The process of remembering a dream requires attention and effort. And if a person does not make an effort to recall and rehearse the dream immediately upon waking, the memory of the dream is likely to fade rapidly as the brain becomes engaged with waking thoughts and activities. The interference from waking thoughts is particularly strong when a person wakes up and immediately starts thinking about their plans for the day, checking their phone, or engaging in other activities that demand attention. And this interference can make it difficult or impossible to retrieve the memory of the dream. The fading of dream memories is also related to the phenomenon of state-dependent memory, which is the observation that memories are often easier to recall when a person is in the same mental or physiological state that they were in when the memory was formed. Dreams are formed during sleep, which is a very different physiological and neurochemical state from waking consciousness. And this difference in state may make it more difficult to retrieve dream memories during waking. The brain state during sleep is characterized by different patterns of neural activity, different levels of neurotransmitters, and different patterns of connectivity between brain regions, compared to the brain state during waking. And these differences may create a kind of barrier that makes it harder to access memories that were formed during sleep. Some dreams are remembered better than others, and several factors can influence how well a dream is remembered after waking. Dreams that occur during the final REM period before waking are more likely to be remembered than dreams from earlier in the night, possibly because the person wakes up directly from the dream and has less time for the memory to fade. Dreams that are particularly vivid, emotionally intense, or personally meaningful are also more likely to be remembered, possibly because these dreams engage the brain's attention and memory systems more strongly, and because they are more likely to be rehearsed and thought about after waking. The act of trying to recall a dream immediately upon waking and the act of writing down or talking about a dream can help to strengthen the memory and make it more resistant to forgetting. Although even with these efforts, many dream memories will still fade over time. The limits of scientific understanding of dreams are considerable. And despite many years of research using advanced technologies and methods, there is still much that is not known about why dreams occur, how dream content is generated, and what functions dreams serve. The study of dreams is challenging for several reasons, including the fact that dreams are subjective experiences that cannot be directly observed or measured by an outside observer, and the fact that dream reports are retrospective accounts that may be influenced by forgetting, reconstruction, and interpretation. Researchers who study dreams must rely on people's reports of their dream experiences. And these reports are necessarily incomplete and may not accurately reflect the actual experience of the dream. The process of reporting a dream requires the person to translate a subjective, often nonverbal experience into words. And this translation process can alter or distort the memory of the dream. Another limitation of scientific research on dreams is that the brain activity that occurs during dreaming is complex and involves the coordinated activity of many different brain regions. Current neuroimaging technologies, while advanced, can only provide a limited view of this activity. Electroencephalography can measure the overall patterns of electrical activity in the brain. Functional magnetic resonance imaging can measure changes in blood flow to different brain regions. But these techniques have limitations in terms of their spatial and temporal resolution, and they cannot capture all the details of neural activity that are relevant to dream generation. The brain, during dreaming, is engaged in a complex set of processes. These processes involve the firing of individual neurons, the release and binding of neurotransmitters, and the formation and strengthening of synaptic connections. And these processes occur at a level of detail that is difficult to observe with current technologies. The question of why dreams have the content that they do, and why a particular person dreams about particular things at a particular time, is still largely unanswered by scientific research. There is no comprehensive theory that can predict what a person will dream about on any given night. Research has identified some general factors that influence dream content, such as the incorporation of recent experiences, the processing of emotional concerns, and the reactivation of memories. But the specific content of any individual dream remains unpredictable and appears to be influenced by a complex combination of factors, including recent experiences, long-term memories, emotional states, and the spontaneous activity of neural networks during sleep. The unpredictability of dream content is related to the fact that dreams are generated by a complex, nonlinear system in which small changes in initial conditions can lead to large differences in outcomes. And this makes it difficult to develop precise predictions about what will be dreamed. The function of dreams, or whether dreams serve any adaptive function at all, is another question that remains unresolved in the scientific literature. Researchers have proposed many different theories about the possible functions of dreams, including the role of dreams in memory consolidation, emotional regulation, problem-solving, threat simulation, or as a random byproduct of neural activity during sleep. Each of these theories has some empirical support, but none of them has been definitively proven. It is possible that dreams serve multiple functions, or that dreams are a byproduct of other brain processes that occur during sleep rather than serving a function in their own right. The question of whether dreams are functional or epiphenomenal remains an open question in the scientific study of sleep and consciousness. Why dream content cannot be fully predicted is related to the inherent complexity and spontaneity of the brain processes that generate dreams, and to the fact that dreams are influenced by a very large number of factors that interact in complex ways. The content of a dream is influenced by the person's recent experiences, their long-term memories, their emotional state, their current concerns, their personality traits, and the spontaneous activity of neural networks during sleep. All of these factors combine to produce a dream experience that is unique to the individual and to the particular night on which the dream occurs. The neural activity that generates dreams involves the spontaneous firing of neurons, the reactivation of memory traces, and the combination of elements from different memories and experiences. This spontaneous activity is inherently unpredictable because it is influenced by small fluctuations in neural activity that can have large effects on the resulting dream content. The unpredictability of dreams also reflects the fact that the brain, during dreaming, is operating in a different mode than it does during waking consciousness. With reduced prefrontal control and increased spontaneity in the generation of mental content. During waking consciousness, thoughts and mental images are largely under voluntary control. A person can direct their attention, choose what to think about, and generate mental content in a goal-directed manner. However, during dreaming, voluntary control is greatly reduced. The content of dreams is generated more by spontaneous neural activity and by the associative activation of memories than by any deliberate intention or plan. This spontaneous and associative nature of dream generation makes it difficult to predict what will be dreamed, because the connections between different memories and the activation of different neural networks during sleep are influenced by many factors that are not under conscious control. And that may vary from night to night. The scientific study of dreams continues to advance. Researchers are developing new methods and technologies that may provide deeper insights into the brain processes that generate dreams and the functions that dreams may serve. Advances in neuroimaging technology, in computational modeling of brain activity, and in the analysis of dream content are all contributing to a better understanding of dreaming. But there are still many fundamental questions about dreams that remain unanswered. And it is likely that the full understanding of dreams will require continued research and the development of new approaches to studying this complex and fascinating aspect of human experience. The gradual softening of dream awareness as sleep deepens is a natural process that occurs throughout the night. As a person moves through different stages of sleep, this gradual softening of awareness reflects the changing patterns of brain activity that occur as sleep progresses. From lighter stages to deeper stages, and then back to lighter stages in cycles throughout the night. At the beginning of sleep, as a person is first falling asleep, there is a transition period in which consciousness begins to fade, and the person moves from wakefulness to sleep. During this transition period, the person may experience brief dreamlike images or thoughts. These are sometimes called hypnagogic imagery. These hypnagogic experiences occur as the brain is transitioning from the waking state to the sleeping state, and they represent a kind of intermediate state of consciousness in which the person is not fully awake but not yet fully asleep. As sleep deepens and the person moves into the deeper stages of non-REM sleep, the level of consciousness decreases further, and the brain enters a state of very low activity, in which there is little or no conscious awareness and little or no mental content that can be recalled upon waking. During deep non-REM sleep, the brain is in a state of rest and restoration. The patterns of brain activity are characterized by very slow, synchronized oscillations. These oscillations reflect a low level of neural activity and a deep state of unconsciousness. The deep sleep that occurs during the first part of the night is the most restorative stage of sleep. During this stage, the brain and body are engaged in processes that repair tissues, consolidate memories, and restore energy for the next day. As the night progresses and the cycles of sleep continue, the periods of deep non-REM sleep become shorter, and the periods of REM sleep become longer. During the REM periods, consciousness returns to a higher level, and dreams become more vivid and more complex. The REM periods that occur later in the night, particularly in the early morning hours before waking, are often the longest and most intense. The dreams that occur during these periods are often the most vivid and the most likely to be remembered upon waking. As morning approaches and the person begins to wake up, the level of consciousness gradually increases, and the dreams that occur during this time may be experienced with a higher level of awareness, and may include some degree of metacognitive awareness or even lucidity. The cyclical nature of sleep, with alternating periods of non-REM and REM sleep, means that the level of dream awareness and the vividness of dreams vary throughout the night. This variation reflects the underlying changes in brain activity that occur as the brain moves through different stages of sleep. The gradual softening of dream awareness as sleep deepens is a natural part of the sleep process. It reflects the brain's need to enter states of deep rest and restoration, during which conscious awareness is minimized, and the brain's resources are devoted to restorative processes rather than to the generation of conscious experiences. The fading of awareness during sleep is accompanied by a fading of responsiveness to the external environment, a fading of critical thinking and logical reasoning, and a fading of self-awareness and metacognition. All of these changes are part of the normal transition from waking consciousness to sleep. The experience of falling asleep and of being asleep is characterized by a gradual letting go of waking consciousness, a gradual relaxation of the body, and a gradual withdrawal of attention from the external world and from the concerns and activities of waking life. This gradual process of falling asleep is accompanied by changes in brain activity that can be measured using electroencephalography and other neuroimaging techniques. The brain waves during waking consciousness are fast and irregular, reflecting a high level of neural activity and active information processing. But as a person begins to fall asleep, the brain waves slow down and become more regular, reflecting a decrease in neural activity and a shift from active information processing to a more restful state. The transition from waking to sleep is not always smooth or immediate. Some people experience difficulty falling asleep or staying asleep, but for most people, the transition occurs naturally as part of the body's circadian rhythm and as a result of the accumulation of sleep pressure throughout the day. The gradual fading of awareness that occurs during sleep is accompanied by changes in the neurochemical environment of the brain, with decreases in the levels of neurotransmitters such as norepinephrine, serotonin, and acetylcholine. These are chemicals associated with wakefulness and alertness. At the same time, there are increases in other neurochemicals that promote sleep and reduce neural activity. These neurochemical changes help to create and maintain the state of reduced consciousness that characterizes sleep. They also help to regulate the transitions between different stages of sleep throughout the night. The neurochemical environment of the brain during sleep is different from the neurochemical environment during waking. And these differences contribute to the distinctive characteristics of sleep, including the reduced responsiveness to external stimuli, the reduced level of conscious awareness, and the occurrence of dreams. As sleep continues through the night and as morning approaches, the brain gradually prepares for the transition back to waking consciousness. This preparation involves gradual increases in brain activity, gradual changes in neurochemical levels, and gradual increases in responsiveness to both internal and external stimuli. The transition from sleep to waking is often accompanied by a final period of REM sleep and dreaming. The dreams that occur during this final REM period may be interrupted by the process of waking, sometimes leaving the person with a vivid memory of the dream that was occurring at the moment of waking. The transition from sleep to waking involves the gradual reactivation of the brain's monitoring systems, the gradual return of self-awareness and critical thinking, and the gradual re-engagement with the external environment and with the concerns and activities of waking life. The process of waking up is accompanied by changes in brain activity that can be observed using neuroimaging techniques, with increases in the frequency of brain waves and increases in activity in brain regions that are involved in alertness, attention, and conscious awareness. The transition from sleep to waking is not always complete or immediate. Many people experience a period of grogginess or sleep inertia upon waking. During this period, they are partially awake, but not yet fully alert. During this transition, the brain is gradually shifting from the sleep state to the waking state. This shift involves changes in neural activity, changes in neurochemical levels, and changes in the patterns of connectivity between different brain regions. The gradual nature of the transition from sleep to waking reflects the fact that sleep and waking are not simply on-off states, but rather represent different modes of brain function that exist along a continuum, and the transitions between these modes are gradual processes involving coordinated changes in activity across many different brain regions and systems. As the night deepens and the brain gently drifts into sleep, neurons slow, memories begin their quiet work, and dreams softly take shape. There is nothing to follow, Nothing to solve. Only the natural rhythm of rest. This is the space where the mind restores, where emotions settle, where dreams unfold. In calm, silent motion, may your sleep be deep, your mind at ease, your dreams gentle, and your rest complete. When morning comes, may you awaken clear, restored, and renewed. Good night, and sleep peacefully.